So thanks everyone for coming. I know it's like 5:30 p.m. It's almost 6 p.m. dinner time, etc. So I really appreciate you being here. I'm just curious, how many people have used Rekognition and built something with it? Is there anyone that's new to Rekognition that hasn't used it before? Okay, awesome. So the title here is a little obtuse, if you will. You know, unlocking media workflows with Rekognition. What does that really mean? And you know, as many of you that have used Rekognition know, over the past year, we've added a whole bunch of new, say, API endpoints and options. We added OCR last week. But you know, most of the initial use cases were extracting object labels or doing face collections, etc. But really what we're starting to see now is that quite a few customers are looking at the labels that come out of Rekognition and then trying to figure out, how do I normalize these labels? How do I use this like with my own taxonomy, for example? You know, maybe I don't want people, person, maybe I want human, for example. And then how can I do other things like clean up the data, the images, etc., before I actually funnel this into Rekognition? And then the other thing is, if I'm getting labels back, you know, potentially I could utilize those labels as a way to figure out how I should, say, transcode my content. So if I have a digital supply chain and a lot of media moving through that, and it's maybe user-generated content, and these are small files, but I really want to optimize the speed at which I transcode, create proxies or whatnot. Maybe I want various encoding profiles that are keyed off of the labels that are coming back from, say, the media that's been landed. So, you know, maybe labels where most of the frames are identified as humans, or people. I'd want to use a different encoding profile to say things that are associated with maybe action content, if you will. So just about me, my name's Konstantin Wilms. I work on the M&E team, so a lot of these kind of use cases that we see, you know, we try and condense down into things like reference architectures. We built a reference architecture for Rekognition. You know, you could take that, deploy it, and then some of these concepts are interesting things to maybe build on top of that, or if you have a pipeline, you know, potentially look at ways to enhance that. So a lot of this is fairly explanatory, right? But I think the interesting thing that drives these use cases for us in terms of reference architectures and things like that we build is the scale of content that we see on the media side, customers landing, be that UGC or you know, content, say feature film content, etc. And then the need to extract some kind of automated metadata. So if it's an asset management system, you know, maybe one of the impetus points there are, could we look at automatically curating this content and tagging it with metadata, and then maybe we don't need a first set of QC people to look at that data before it gets into the asset management system. You know, maybe we could put it in different bins and then have different people that are specialized in those areas classified after that. You know, so we at least on the media side, there's obviously a lot of image data. So if you look at a lot of the media companies, many are bringing full image archives onto AWS and then storing like all the high quality assets in Glacier and maybe the proxies or the deliverable assets, if you will, on S3 or S3IA. And similar for you know, media content as well, right? So we're seeing a big shift from you know, what was maybe smaller amounts of media content to a large amount of VOD. You can also look at things like elemental media services. So there's a lot of impetus for live content to come in, get recorded, and then maybe run through things like Rekognition. So the question here is, you know, if we're extracting these labels, that's great, that enriches the content potentially or helps enrich it. But what about using those same processes, you know, maybe it's Lambda functions that we have as part of the supply chain or a pipeline, using that to enhance, or that data as a feedback mechanism. And if we look at just a simple pipeline, right, there are potentially things we can optimize on the ingest side. There are things that we could optimize on the storage side, and then obviously pre- and post-analysis to basically look at enriching the data, cleaning up images, denoising, all of these other approaches to processing that. And then actually, skip to there, using that as a feedback loop back to our storage system. And then potentially we can use that to reprocess data. So like one example that I'll talk about is potentially images that have a lot of fog in them, and that's part of, maybe it's a camera artifact and it's not a content artifact. Rekognition would identify a lot of these types of things as atmosphere, as a tag coming back. We could look at that and see, okay, we're not expecting to get this content, run like a Retinex algorithm against it, pass it back to Rekognition, and then we actually remove that noise off the front of the image and get back valid labels. So these are interesting use cases here. And the other thing here is obviously why would you do this as a managed service? If you think about all of the Rekognition endpoints, if you will, you should look at each one of those. If you built that out as a service from the ground up, maybe using TensorFlow, et cetera, whatever the models and frameworks are, you have to be concerned with versioning, updating, blue-green, deploying, all of these pipelines, and then maintaining a velocity. So, one of the key things with Rekognition is that if you have facial collections, you can scale up to 10 million faces. If you're passing in image data, it could be coming off of S3 and the service knows how to parse it. But the other thing is the deterministic nature of passing in image data. So, depending on the size and type of image, I know I may get a response back in 500 milliseconds to 2 seconds. So that kind of deterministic response rate for things like supply chain, user-generated content, you don't want to have to wait for something like an autoscale group to spin up to facilitate that. And then all of the native key endpoints that I'll talk about too. So for those that are new to Rekognition, a lot of these APIs have different, obviously, use cases, right? But the primary ones that are useful from this particular perspective are object and scene detection, and potentially text detection as well, for where we can't get accurate object and scene confidence returned. Facial analysis, et cetera, to a lesser extent, although those can also be used as feedback mechanisms. The same with image moderation too. And then the applicability here, also for those that are new to this in the media space, is that there's definitely the ability to reuse a lot of the code. So if it's Docker containers you're building, if it's Python code in Lambda, if it's Node.js, whatever it is, that code base that you build can start being reused for different purposes. So the Python code that is used for, say, maybe a supply chain process to pass an image to Rekognition and then funnel the output data into Dynamo, that code could be repurposed for, say, local editing, where as images land on, say, a local file system, you could run the same Python script, but instead of injecting data into Dynamo, you're maybe re-injecting it into the EXIF data on the images. And then your editors that are using, say, local Windows or Mac or whatever their tools are, they could have a local file system search or asset search in the applications they're using. So we see a lot of that, everything from Mac OS Finder to injecting tags there, to things like Premiere, JSON automation, et cetera, and Photoshop, et cetera. So very useful from that perspective. And then the other thing we frequently see is Rekognition is very easy to get up and running with, make API calls, get data back with confidence scores, and then do whatever we want with it. But there are considerations across these, if you want to look at this as boundaries or pillars within, say, supply chain or media processing. So on the content side, dealing with different file formats. We need a way to normalize the data, like maybe it's different streaming protocols, for example, right? Or MP4s or AVIs or whatnot. We need some way to normalize that before we pass the data to Rekognition. On the processing side, obviously the storage and networking. So if we wanted to do image cleanup and we're maybe using ECS and we're hydrating the content, say from S3 to EFS, to then run workloads against it to maybe clean up the content, transcode it, whatever we're doing. Obviously the storage and network I/O is important for this. And that directly relates to I/O for actually dealing with the data. Because if we're getting 500 milliseconds to say 2 seconds, and that's deterministic, we don't want to skew that number, by having a high latency hydration as part of this process. So that's kind of key to that too. And then on the quality side, it sort of relates to the processing velocity. So with things like supply chain, many of our customers will look at our on-prem SLA that we created was maybe 24 to 48 hours with a lot of manual processes. Now that we have it on AWS, we want to reduce that to a couple hours. And the goal here is to do that deterministically, but also with the processing velocity. So in other words, if we can do more scale, we want to land more content. Maybe it's hundreds of terabytes a day. But we expect as that grows, the back-end infrastructure should be deterministic. So everything should still work at the same pace. So this is kind of key for Rekognition here in like one of the benefits that it provides. And then conformance is another thing too. So not only say being able to ingest the content, but then conforming it for local use. So maybe we want to perceptually compress the images before we actually store them. And that can save on cost on S3. And then just on the integration side, there's some obvious ones, but it really depends. A lot of the B2B or B2C systems out there, some of them will utilize a CMS, others are going to be a traditional MAM or DAM. And then there's also the option of where do we store the labels? Do we use Dynamo? Do we inject that back into, say, the MP4 headers? Or do we have sidecar data and maybe Athena's running on top of that? We have QuickSight that's used to interrogate that as well. So these are all, I'd say, things that are worth looking at before just jumping in and utilizing or integrating Rekognition into a pipeline. And then just to look at the, the things that are relevant here, right, from object and scene detection. Really the important thing here is that you're not only identifying objects, but you're also identifying scenes and also concepts. So, it sort of goes from sky versus mountain to mountain range to, outdoor location, those types of content or concepts, if you will. On the, at least facial analysis side, so some of the feedback loops that we could do is we could look for objects in images instead of passing everything for facial analysis. But if we look for objects in images, those objects that come back may be detected as human, with high confidence, or person, or people. The thing that we could then do is if we have a, say, Lambda step function pipeline, is basically take that and only then pass that for facial analysis. So if our object label returns that there is a person in the scene, go off and make a secondary API call as a second step in a step function framework, and then go and look for facial analysis features. And the reason I say two-phase instead of doing that one time is that if you do, say, facial analysis using Rekognition and you want to return all of these details, for example, not just facial landmarks, but maybe general attributes, like is a person smiling or not, what the demographic data is, what the age range is, that can also increase the processing time. And it's not a lot of processing time, you measure this in, say, hundreds of milliseconds, but if you multiply that out for, say, a large image archive, this could skew it by potentially days, depending on if you have not optimized these calls. And then the other useful thing here is, at least from Rekognition, from ability to use feedback loops, is obviously the moderation labels, so the detection of explicit or suggestive content, and then celebrity detection. It's worth noting that celebrity detection works against IMDb, so it returns an IMDb URL to those actors. But there are a lot of use cases we see where we get the question, what about my indie production where I know my actors, but they're not part of IMDb, they're not in there yet. Potentially it's a whole bunch of actors for different shots or programs, but they're more indie level. Maybe they're targeted for, say, YouTube or other OTT platforms. That's actually a great case for using the celebrity, or at least not the celebrity detection, but collections, right? So the goal there is to basically name each of the actors, at least their facial images or photos or headshots, put those in S3, create a collection, index all the actors against that, with the backlink being to the location on, say, Dynamo, with all of their details, for example. And then for each one of these, detected images that come through showing person, for example, do a facial comparison against our home-built collection. So it allows you to build your equivalent of a celebrity detection for, say, indie use, for example. Just on the topic of best practices further on that, there are limits. I'm not going to talk about the limits here. Those are well documented. But I think if you look at the Rekognition limits and then you try to figure out what is the implication of this when I'm, say, doing high-speed processing or having to process a lot of content. Like I said, operations are fairly deterministic, so you can take that into account for how long it'll take to process batches of images. S3 is optimal versus doing inline calls. However, if you have the content locally, then it's maybe more optimal. If you have it local for, say, Photoshop or other editing purposes, it may be more optimal not to move it to S3, but to maybe compress the image and just make a direct API call. There's some other things, too, that you can do when images arrive, and this is more particular for user-generated content. If the image is less than 80 pixels, it's fairly certain we won't get much detail out of it. So you could scrub those immediately, saving having to make an API call. And then there's some other things, right? So you at least want 1024 pixels. If you're processing, say, 1080p frames, you need a 40 by 40 pixel, minimum resolution for faces. So it's all these things to bear in mind as you pass content into Rekognition. And like I said, the reason I listed this here is that often we'll see people, or at least customers, will come back and say it doesn't appear to work for use case X, Y, and Z. And in many cases, it's some of these types of things that have been a malfunction in that process, if you will. And then finally, most of the like the CLI and API components that we have will do a fairly good job of throttling. But if you need to process a lot of content in batches simultaneously in a parallel fashion, you could look at things like first hitting Dynamo and then using Dynamo streams and utilizing Lambda off of that to then go and make the calls. So in other words, instead of making a direct call to Rekognition, you're potentially just putting the asset ID of where the asset is in S3 into Dynamo and then using streams. Another great way is to use Kinesis streams as well and basically shard that out. And the reason for that is to basically, if you look at the graph on the right-hand side, and we have I think we have part of the architecture blog, actually has a fairly lengthy article on this, on exponential back-off and control. One of the approaches here that you could look at doing is exponentially back off as API calls fail, but combine then that with jittering the calls that are made to try and push more data through the APIs. And you can basically see there's a there's a fairly linear curve of as you start adding these other ways to alleviate API blockage, if you will, you're able to get more throughput through the system. So it's definitely something to look at. I talked about most of the AWS services that would typically be utilized here. There are also asset management, media workflow, content processing, typical use cases. But the other thing that we've seen a lot is, what's the best practice, or how can I go about building some kind of a toolkit to do a lot of this work for me? So I'll talk about, OpenCV, ImageMagick, FFmpeg, and then some other libraries, and basically how to componentize those and build, like, say, a Swiss Army knife for doing cleanup before you make those recognition calls. I talked a bit about this, in terms of complementary services, so, that whole end-to-end supply chain, if you will. You could look at media processing, so say the elemental services to create proxies, to then rip frames out of storage on S3, decoupling the infrastructure here, so decoupling when the files arrive from where they're actually processed using, say, SNS, SQS, etc., fronting things with API gateway, and then potentially handing off to batch or ECS or plain EC2 as well for processing. And then the last piece to basically maintain context as you move through these workflows is DynamoDB. So just to get to an example here, and so the rest of this will be around how would we take a video clip, and this is an open source movie, Tears of Steel. So I basically looked at this, and then how would we take these best practices or requirements that we've seen come from customers and construct something to solve those problems. So what is the process or the best process for processing this as an example input? So the one thing we can do to start off is we could just extract all of the frames, right, and pass those in. Maybe we extract, and this is using FFmpeg, so extract each 10th frame, or one tenth of a frame per second. The other thing we could do is we could extract the iframes. And there are different use cases for this. So if you think of potentially a use case like, say, C-SPAN or that type of long-running camera ingest against, say, political figures or talking heads, maybe sampling each 10th frame is a good way to make sure that we're tracking the same person over time. We could potentially use iframes, but it now is determined by what the length of the GOP is and what the duration is between those frames. And the third option here is we could do scene change analysis, right? So only extract frames when we detect that the camera has changed location or there's been a cut from one shot to another based on the difference between those pictures. And the reason for this is we see this a lot as well. So the one approach is I'm just going to extract everything, or I'm going to extract a frame every 3 or 5 seconds. That alleviates the API calls, but it's still a lot of data, right? So if you look at VOD clips and running those through Rekognition, a 30-second ad is 900 frames. That's 450 megabytes potentially of data, and then all the API calls that you have to make for that. And that multiplies out as you get up to, say, feature length. So there's some things you can do. You can reduce the capture rate, but maybe that also decimates our accuracy that we're trying to get here. Because the one thing, if you extract a frame every, say, 3 or maybe 5 or 6 seconds versus doing scene change analysis, you may get the wrong frame, or you may get a frame 6 seconds into that scene. So that's potentially problematic for detection too. So this assumes no post-processing, but these are typically the payloads that we would see from this. Now this is one file. If you had a whole bunch of content arriving and landing on S3, this impacts your S3 storage, it impacts your I/O against your S3 partitions, etc. You may have to look at how you're partitioning the data. Are you putting a hash in front of the file in order to evenly distributed for good I/O. But regardless of that, it's a lot of content, and it's just another problem that needs to be solved. So on the ingest side, I'll get to the previous problem on how we can look at solving that. But the other component here is ingest, right? So how can we do images versus on-demand versus live ingest? So if we're looking at recognition for images, we essentially want to do correction on it. We want to then optimize after we've corrected the data and then process that data, and that may enable us to get higher quality labels out of it. If it's video, we'd be creating a proxy from it and then segmenting that and then actually utilizing the image pipeline to process those images that are coming off that on-demand content. And third, if we're doing live content, one of the novel ways you could look at doing that is potentially landing HLS or dash chunks, or if the encoder can support it, segmenting those files every X amount of seconds. If you're doing something like dash or HLS and it's starting on an iframe, we can potentially take every packet every, say, 5 seconds and just pull that out with FFmpeg and do image recognition against the iframe. So that's an easy way to go from, say, a live stream to either something like Elemental Media Live, for example, or potentially something like Nginx with FFmpeg and build a whole live processing pipeline there where you can inspect and then store those images too. So it's critical here to build these components to be reusable, because if you build the image pipeline, that same code maps well to on-demand, and that same code maps well to live. It's not much of a stretch to add that kind of functionality. On the right-hand side, I think one of the things worth calling out here is that there are some benefits to doing things like extracting only iframes versus extracting a frame every couple seconds. Because one of the problems you could get is macro blocking if the video quality is low quality, which is definitely going to skew performance against calls to recognition, like objects may get missed. The other thing is if your, say, live stream that's coming in that you're then processing has a lot of, say, discontinuity errors or packet loss, etc. Potentially you can still write that all to disk, but you may have loss in the actual transport as well. And that could further skew extracting frames or even being able to extract those. So it sort of brings us to this pipeline in terms of the toolkit, right? So the one thing that can be done here, at least with Lambda, for example, is to take FFmpeg, OpenCV, ImageMagick, and Spacy. Spacy is an NLP processing toolkit for Python that is high performance because it's compiled with Python. But essentially, the good thing here is that if you create a custom compile of FFmpeg, you can then binary wrap that for use by Lambda. The same with OpenCV, that can also be compiled. ImageMagick is native already with Lambda, and then Spacy has to be basically compiled and stripped down. I'll get to that one later, but OpenCV, if you wanted to reduce the size of that in FFmpeg, a lot of the options there are to take out the protocols and codecs you don't need. Most of these have command line options for doing that. But essentially this allows you, or the target here is to build a multi-factor Swiss Army knife that can run with Lambda, that can do any kind of cleanup we want. So we may need to extract frames out of video fragments. FFmpeg would do that. It works great for that, and it'll cope with errors. We may want to do, say, blob or shape detection or cleanup using OpenCV, which is a good computer vision framework. ImageMagick allows us to do things like denoising and so forth, and then Spacy. There are a lot of other options there. It's a good one for Python, but that allows us to do things like label parsing and normalization, if you will, and then semantic comparison between labels. So there's one other thing worth talking about here, and this is, what about the things that we don't have? Like I talked earlier about, what about if we did custom celebrities, or we wanted our own set of celebrities? There are a lot of these frameworks that you could look at. You could deploy this utilizing object store, so S3 on the back end, EFS for hydration, and then potentially our AI armies running, say, TensorFlow, Caffe, whatever use case you want. But a lot of these have already good starting points. So, YouTube 8M has about 500,000 hours of small video clips. So if you're looking to do video analysis with deep learning, that's something worth looking at. Places as different places in the world, there are about 2.5 million images that are labeled. And then similar for the others, CIFAR is about 30 million images, of which about 10 or 100,000, depending on the data set you picked, are already classified. So you can take these, you can deploy them, you could even use things like NVIDIA Digits, for example, which gives you a UI to work against, and run it on, say, P3s or G3s, for example. So getting back to the scene change extraction, I ran this movie just through a scene change FFmpeg extraction with a threshold of 0.4. And the threshold here is if there is a change in the scene as we're winding through all of the frames, if frame A versus frame B has changed by more than a threshold of X, as I believe it's a logarithmic scale, but if it's changed by more than a threshold of X, then we know it's a scene change, extract that frame and store it to local disk. So you can see here there are keyframes that have been extracted using scene change extraction, but the primary thing here is we didn't actually get the title of the movie, and that's because it's a fade from black, and then the title appears, and then there's a gradual fade to black, so that first scene change might for some reason have not been captured. So our first frame is actually, not relevant to the content, right? We also have this frame here that's a side profile view of the actor versus a front profile view. So it's valid for the objects, but it's not really usable for, say, facial detection potentially. And then we have some things that have been extracted that have, from a processing perspective, no context, right? So 40 years later in the middle of the file doesn't really mean anything. But there are some things that were valid, right? So we could do facial detection here or potentially here as well. But the gist of this is, how can we go beyond this and look at cleaning up these frames and maybe normalizing this data set to extract better info from it. So some of the things we can do better is, the first one would be, FFmpeg with a scene change filter is very rudimentary content-aware detection. If there is a change in pixels, store the frame. But there are a lot of other projects that go a little deeper into this. So Python Scene Detect is one, it's an open source project. But essentially, if you think of a scene change, FFmpeg will do that based on pixel boundaries, but there really isn't a scene change per se. So if you look at the graph on the right, you can see some of the dips and ebbs, right? And when it gets to a dip right at the bottom there, that's actually a complete fade to black. But in many cases, if it's a fade over time, over say 1 or 2 seconds, the end of that is not the start of the scene. We want the middle of that. So, that event between at least the valleys on either side of a piece of content, that is the scene that we're looking for. And then secondary to that, we don't want to just capture the black frame right after we've detected it because it's still fading in video content. We actually want to be able to say maybe look after the threshold and grab the first frame. That'll potentially give us better quality. And then there's some other things we could do if we expanded that, right? So the pictures on the top right there is film editing technique, pretty common one, a jump cut. But a jump cut can be useful for things like facial detection. So if we detect that there is a jump cut and there's similarity between the images on each side of that scene change, Potentially, this is something that could be used if we detect labels being person for more accurate, say actor or person identification. So going back to the image sequences, that whole thing of like the jump cut comparison, comparing the two of those. And then the other problem is if we're capturing these scene changes and maybe there is a camera cut to something, but it cuts back to the same scene, we don't want to process or store that same image. So the image at the top left there this is all from one scene, but you can see in the middle, the subject has a newspaper over his face. Beneath that, he doesn't. If we use perceptual hashing against this, which is a way of doing image comparison based on frequency domain, not based on pixels, we can see that between the top one and the middle one, we have a 37 weighted value of difference between those frames, but the bottom one has a 5. So if we use these same thresholds that we get back from Rekognition and apply it in this fashion, we may say, anything over, say, a threshold detection of 10, I'm just going to ignore because it's potentially the same people in the same scene, and I shouldn't waste time reprocessing that. And perceptual image hashing is important because even if there's no movement in the scene, the pixels, if they changed by one hue of color value, the MD5 or the SHA-1 or 256 would be completely different. So the goal there is, how can we do this image comparison not based on traditional cryptographic hash, if you will, and figuring out where the frames actually do change. So the performance on this is really good. If you wrapped this into, say, container, or you put it into Lambda. I think I ran it on like an i5 CPU, and about 65 milliseconds to load two 720p frames, do a differential hash on them, and then compare them and get that value back. Is there an actual change between the frames? So you can process a lot of content without needing a GPU, and then you're basically eliminating these false positives that we don't need to store and we don't need to process with Rekognition. So dhash is the most performant. There are a couple others. Ahash is just an average. It gives a lot of false positives. I would avoid it. Phash has been around a bit. But dhash is, it's more of a comparison of the pixel gradients. So at least the 3 images in the middle there basically describe the process on how this hashing works. We essentially take the source image, reduce the size to a couple pixels, extract the brightness potentially, and then decimate that. And that basically gives us then a matrix of values, either over pixel brightness range or potentially frequency domain. And that's then used to generate a hash for comparison. So the other thing we can do is image correction as a feedback loop. And this one is actually, we get this question pretty often. My image data is potentially dirty, or I don't know the quality of it when it comes in. Is there anything I can do with Rekognition? How would I do more accurate labels there? So at least on the top right, I talked earlier about this, Rekognition returning labels like atmosphere or fog, where you may not really expect that because those are sort of out of the ordinary. And if you then took those labels as part of, say, a step function pipeline and you processed the data, one way to clean up this type of image artifact, if you will, is called Retinex color restoration. So it basically looks at, from a brightness perspective, how to correct the image. And once you funnel it through that, this also does not need a GPU, by the way. It can be done, say, within Lambda. But once you process the image through this, it identifies, or it does a pretty good job of surfacing the details that are hidden. So for things like atmospheric issues like this, or potentially low light, it also does a really good job of identifying subjects or bringing things back where the camera was maybe used in low light conditions. So I've passed images through it, which was shot in close to darkness, run it through Retinex, and then actually the people are identified in the scene. So where would you start here, right? Would you write Lambda functions and then use image magic? I'd say that the best place to start is Rekognition will return sharpness and brightness for images. So you can almost look at that as like a low-cost or zero-cost infrastructure to do a first pass and determine if things are out of whack for color and brightness. And then you could pass it through something like potentially image magic and do a color correction for the histogram, so like normalize the colors, correct the color balance automatically, and then maybe advanced, you would use something like color correct and Python image loader to basically run, say, a Retinex algorithm over the content. There's some other things on the image optimization side. So one of the other, I talked about the image sizes passed to Rekognition. It always helps to pass a good quality image into Rekognition, but potentially, or at least we see it a lot where, there is a limit in the API. So in terms of either if I make a direct call, it's 5 megabytes. If I make a call using S3 saying go process this image, it's 15 megabytes. How do you overcome that if you have, say, 35 millimeter photos, right, that are potentially 50 plus megabyte lossless PNGs? You can compress it down, but that also loses details. So the smaller objects then won't get detected, or maybe the larger objects would get detected inaccurately or with a lower confidence, which is really not something we want coming out of Rekognition. So there are a couple ways around that. One is Beamer that makes a product called JPEG Mini. There's also PNG Quant, which is open source. And then Mozilla has MozJPEG. All of these will do perceptual compression without human visible image loss, which is also useful for deep learning systems. So on the top right there, you can see this particular image has been reduced from 189K to 117K, so it's quite a reduction. And it's very hard to make out the difference. That's a zoomed in part of it. But if you look closer, the projector doesn't really reflect it, but there is some dithering on the edges that's been introduced. But you would only see that if you really zoom into it. So how does this help? So this image has been cleaned up with the first pass with Retinex correction, and then passed into face detection. And I think the important thing here is that you can see the one on the left has an age range detection or estimate of about 4 to 9 years old. It's clear this is not a 9-year-old subject, but if you then look at the one on the right, it's now more accurate because we have better details in the picture. At around 4 to 7. The other things that are important here is the confidence factors have gone up now as well. So not just the looks like a face, but our smiling has gone up from 98.1 to 99.9. So this is very important from that perspective because for a lot of at least Rekognition operations, you'll want to set a threshold and keep that really high. So that you don't have false positives return that are at a lower threshold. So that's all the image processing piece, right? So I was thinking maybe it's interesting to talk about dogs, cats, and bananas. But essentially the concept here is like the terminology or the labels that come back from Rekognition. How do we apply our own custom taxonomy over that? So we have a lot of customers that maybe use this for large image archives, and they already have a taxonomy, and they really want to align those labels with their internal way of tracking assets, etc. So maybe everything that's identifies a person, person, child, etc. They just want to classify that as human, for example. So one of the ways around this is to use NLP with Lambda. As a way to basically calculate the semantic similarity. And it's a big advantage to doing it this way versus trying to keep lists and arrays of words and then trying to match across that via something like regex. It's a lot faster than that. So one of the examples here is to use something like Spacy, which is I talked about earlier. So it comes with a bunch of models that you can use for NLP modeling. I think like one of the important things here is that these models are done as high performance, and then you get vector comparison against them. But the corpus or the size of words, etc., is about 680,000 individual words. So from a very basic perspective, this can be really useful, right? So on the right-hand side is using Spacy for simple sentiment analysis. So essentially all of the labels that come back from Rekognition, we assign as tokens and put into Spacy, run NLP against it. And this is actually using a higher order level framework called Textacity, which is sort of built on top of Spacy as a lower level framework for NLP, if you will. But essentially this gives us a bag of words returned by weight. So we can see which are the most common things that are coming back from this video clip if we're collecting all of these labels. On the bottom side, you can see, or at least the bottom line piece of code there, is basically similarity scoring. So we basically want to look at, essentially we have, car, boat, motorbike, but we have, say, a genre for the media we want to process, and we want to identify things such as vehicles. We can then iterate through these labels and then get a semantic similarity returned on those tokens. So the same way that Rekognition classifies objects by confidence score, Spacy does the same thing for words. So you can take those returned object identifiers and their confidence scores, take the words, and then compare that against, say, something you're trying to figure out, are all these things that have come back from this frame similar to this topic I'm trying to model. Then the last thing here, just before I get to the summary, is the label data storage, right? So where do you store the data and how should you store it? Anything coming back from Rekognition. So at least the one thing to do, especially with the video frames we're analyzing and the fact that we're maybe doing scene change analysis, is to basically store maybe the wall clock time if it's live, or potentially store the SMPTE timecode offset. So if we're using FFmpeg, it will actually return the PTS offset, so the packet stamp offset. So that's very useful. And then we can actually do things like inject that data into Elasticsearch and or DynamoDB. So the benefit of using it this way in Elasticsearch with more data in addition to these labels that we've normalized is that we can then do fairly common searches across that and then find out over time where do these words or where do these terms occur. One thing I have seen is that customers often ask, should I scale up, should I size my cluster for Elasticsearch to a certain size? Well, the one way you could look at it is if you have a supply chain and you're landing content in it and you're using Elasticsearch for maybe an operator dashboard, is to potentially use smaller clusters with the data and then prune those collections using something like Elasticsearch Curator over the top of that. So essentially that gives you, for those that are familiar with MongoDB as an example, pretty close to the notion of a capped collection, where we sort of have the sliding window, but we don't have to allocate potentially a lot of resources or do a lot of cleanup over time. So just getting back to taking Spacy and Textacity and then identifying these tokens across this video clip, right, or this trailer. If you look at the one on the left, that's the non-normalized version. So essentially, we have a lot of people, human person, that's great, but it's not really useful because I can't really extract any pertinent information out of that. But on the right-hand side with NLP modeling, We reduce it to basically statistical analysis, and then we can move the high watermark and the low watermark out. And you can then see that some of the terminology, like military, for example, is better exposed. So given that the clip is sci-fi movie trailer, these are much more relevant labels that have that we got back. So just to wrap up, we can sanitize the media, but that actually enables us to get better confidence scores and better positives back from Rekognition, versus having to maybe do multi-stage cleanup on that data. But the types of things that we could do, since we then have normalized this data, essentially we've used the scene changes, etc., to basically visually topic model this data, right? So it's got a lot of use cases from there. We could potentially use multi-stage transcoding, or we could then pass a genre or with an encoding profile to re-encode content a certain fashion. We could also do timeline-based discovery. So if you think of, what if you wanted to build something like X-ray, which Amazon Video has, right? One of the options here is to do the scene change analysis, and then look at things like those jump cuts where the actual scenes are, and then do multi-pass against the actors. Is it a person? Okay, let's go and do celebrity detection or detection against our own internal data set in a collection, and then utilize that as a way to build something like a X-ray type service. So pretty useful from that perspective. And then lastly, if we are getting labels back, so say for example, atmosphere is a label, we could use that as some layer of intelligence, if you will, in order to drive cleaning up our content, such as Retinix algorithm applications there. So with that, thank you. There are a couple other sessions that are very much related to this one, also on the Rekognition genre, if you will. I think there's also a workshop coming up, so definitely check these out too. So thanks, and I'll take any questions. Yes?
So regarding sentiment analysis, how accurate is it when you actually have to classify it based on a theme or a genre, right? Because objects like cars, for instance, are there in most movies. You have to differentiate between a drama versus a romance. How would I do that?
So yeah, so the question was, how accurate would this be for something like sentiment analysis, where most of the objects coming back are objects? So I think that's where you would look at using the NLP processing to differentiate between the objects as labels and other things like the concepts and scenes. So Rekognition will give you back all those labels, but it's often very hard to tell without looking at it with NLP, the difference between an object and a scene or a concept. So if you were to use that as a way to separate that, you could essentially just drop all of that data on the side, and then you've extracted your scenes, for example, or concepts. And the thing is, you can also then use that as like a second and third dimension for tagging that in, say, an asset management system, because that's more beyond what you'd have with simple object tagging.
Just one follow-up question.
Yeah.
Moving away from images and onto video content, would the tool actually work for a use case where I have to scrape the video for rolling credits to extract metadata about the cast and crew?
So the question was, could this work for extracting rolling credits? So yes, but that would be a technique where you may look at the scene changes, and then your credits are going to roll last, and there's typically not a scene change. But since it's flipped to credits, you know where the boundary start is of that in terms of the frame offset or the time offset. And then basically use that and then extract every single frame after that, and then pass that through OCR recognition. So yeah, so the OCR functionality on Rekognition does a really good job of fonts and typefaces, even handwritten words, for example. But it also does a good job of if the lettering or the typeface is being rotated, tilted, or pitched. So it'll give you confidence scores back on its ability to determine, I'm 80% confident that this is word X. So if you have, for example, a logo, and maybe the O is replaced with a graphic or something as part of, say, a branding logo, it may infer that that's an O, for example, but it may be a lower confidence because of that. But you take that output and then potentially process that using NLP. Yes?
Simple processes like enhancing contrast or sharpness improve recognition by a lot. Why don't you run them internally before you run the recognition algorithms?
Internally, you mean as part of recognition? Yeah, that's actually a good question. So the question was, why aren't these image processing algorithms run internally as part of recognition, as part of, say, a pre-cleanup? I think maybe one of the reasons there is that what's to prevent the image processing it the wrong way, and then you basically are creating garbage to feed through the system. So I think one of the concepts there is the other thing is it no longer becomes deterministic, right? Because how many stages in your pipeline do you then need to process this image data? And that would, going through that pipeline internally, would then affect the deterministic nature of returning those labels. So doing that at a huge scale may mean that that particular feature, which is a really good feature for recognition, may be skewed, or you may not have control over that. So Lambda's really good at like 100 milliseconds, like all of these things I talked about, the cleanup, even the more advanced ones, like say RL filters for image magic, that look at doing like say an unsharp mask in the content without embossing the edges. Even those will execute within a couple hundred milliseconds max. It depends on the image size, on what you're doing and what that image magic script looks like. But Lambda's a really good fit for that if you're not dealing with huge images that you have to slice up. Like if it's gigapixel images, you want to funnel that through something like ECS or containers or AWS batch. Any other questions? Nope? Oh, sorry. So the question is it possible to differentiate between someone holding a photo versus the person themselves using depth analysis? So if you do facial analysis with recognition, and this is typical for things like authentication, where someone walks up and stands in front of a webcam, recognition will not grab the people behind, and it's not because of depth, it's because it grabs the largest face front and center first. So that can be a benefit in this use case or could potentially not be a benefit. But one of the things I listed on the facial analysis slide in terms of crowd detection, that allows you to do a pass an image in, and we return up to 100 faces. If there are 101 people in that shot, that 101st person will have the smallest pixel density face, so X by Y. So it sort of goes from the largest working its way through to the smallest.
What if the person holding the photo is out of the image and they essentially use the face as a method for authentication, if that's what recognition is being used for?
Yeah, so if you're passing, the question there was, and I guess this is, could this be used as a way to, bypass an authentication system? It entirely could be used for that because it's not a biometric process, right? So the facial detection is based on, and it's really hard to think of, is there a way to do that? You couldn't do that via color correction because if I held the photo at the right location, it may be valid from like contrast, sharpness perspective and color perspective. Maybe the one thing you could do is get multiple shots of the same person. So in other words, in order for you to authenticate successfully, we need to grab 3 photos of your face, and we need to make sure that everyone is at a different level of accuracy. So the watermark would be like, say, I think there's a default of like 90%, maybe 85%, and I expect to see at least a 2 to 3% differential between the first, second, and third face. And that way, anyone holding up a photo, even if they tilted or pitched it, Rekognition will look and it'll see, the pitch, yaw, tilt, azimuth, etc., and track for that and align it correctly. Those would all be within the same maybe 1%. So you'd be able to say, this is someone holding up a photo and trying to move it around to get through the system. Sure. Any other questions? Nope. Thanks.